Hey everyone, and welcome back to The Explainer. Today, we are putting on our detective hats and stepping straight into the laboratory. We're going to investigate a very bubbly, honestly kind of mysterious phenomenon that you might know by its nickname, elephant's toothpaste. When certain substances get mixed together, this wild, intense reaction happens. Bubbles violently appear everywhere, and it leaves us with a really fascinating fundamental puzzle. We have to figure out exactly what new substance was just created. But, well, how do we actually do that when our biggest clues are completely invisible? We're going to break down the evidence, analyze the property data, and solve this mystery step by step. Let's get into it. Okay, let's dive into this. Here is the scene of the crime, so to speak. We start by combining potassium iodide and hydrogen peroxide inside a flask, and that flask is sitting right on a digital scale. Initially, the scale reads 277.4 grams. But once that reaction gets going, the mass literally drops to 274.9 grams. We have seemingly just lost exactly 2.5 grams of matter. But, matter doesn't just vanish into thin air. Or does it? Actually, this sudden drop in mass is our very first major clue. So, to understand this case of the missing mass, we really need to talk about systems for a second. If our flask was a perfectly closed system, meaning it's tightly sealed with absolutely nothing allowed in or out, that mass on the scale would stay exactly the same. No change whatsoever. The laws of science guarantee us that matter cannot just be destroyed. But the mass of our partially open system, where that potassium iodide and hydrogen peroxide were combined, decreased. And that tells us something absolutely critical. A new substance, specifically a gas, is being formed, and some of it is physically escaping the system. Our suspect is on the loose. If you actually watch this reaction closely in the lab, you get undeniable physical proof of this escape. If you place a stopper just loosely on top of the flask, it will literally start to rattle. It's such a fantastic visual. And that rattling isn't magic, right? It's concrete, undeniable evidence that matter is flowing out of the system. The newly formed gas is made up of particles that are way too small for us to see, but those particles absolutely have mass, and they are aggressively and honestly quite noisily pushing their way past that stopper and escaping right into the room. All right, moving right along to the glowing ember test. So, we know a gas is escaping, but what exactly is it? The air around us is full of all sorts of invisible gases, so we need a reliable way to identify this specific escapee. When we manage to trap some of this mystery gas and introduce a glowing ember, the results are explosive, literally. The gas produced makes a glowing ember just completely burst into flame. And if you put an already burning flame into the gas, it glows noticeably brighter. This is a massive, absolutely unmistakable clue. Whatever this invisible gas is, it aggressively feeds and expands a fire. Now, in the lab, we don't just set things on fire because it looks cool, although, come on, it definitely does. We do it to gather flammability data. You see, every single pure substance has characteristic physical and chemical properties that can be used to identify it. How a substance interacts with fire, whether it smothers it, totally ignores it, or violently feeds it, is a characteristic chemical property. So this flammability data is a vital piece of scientific evidence in our ongoing investigation. Now, what's really interesting about this slide is how we actually put this data to work. Flammability data is incredibly powerful because it helps us quickly identify the types of gases that aren't being produced in this process. Think about it. If we have a list of common gases, and we know certain gases definitely do not feed a fire, we can confidently cross them right off our suspect list. We use the positive characteristic of our mystery gas to systematically eliminate all the non-flammable candidates. It's a classic process of elimination. Which brings us to the scientific dragnet. Now, our investigation doesn't just stop because we eliminated a few obvious suspects. We need to tighten that dragnet. This is where we bring in our rapid-fire testing protocol. Testing properties like the melting or freezing point, or measuring the density of the gas, gives us distinct measurable numbers. By gathering this specific data, testing the melting and freezing point, testing the density, we can identify additional substances that definitely aren't being produced in this process. Basically, if a known gas has a totally different density than our mystery gas, boom, it's off the list. The final step here is perhaps the most crucial one of all. We take all that data and we compare the results of our flammability test, along with the density and freezing point, to results from controls. Controls are our known standards. It's exactly like checking fingerprints found at a crime scene against a known database. Comparing our results to controls helps identify even more substances that aren't being produced. It's the absolute gold standard in science to confirm our findings and make sure we haven't made a mistake in our identification. And this brilliantly illustrates exactly how scientists solve complex mysteries. We apply key model ideas about how systems work, like realizing our partially open flask is losing mass because a gas is escaping, and we analyze patterns in that macroscopic data. By looking at the mass decreasing and thoroughly testing the properties of the gas we captured, we piece together a rock-solid explanation. We figure out exactly which substances could or absolutely could not be produced during the reaction. So, by carefully tracking that missing mass and testing those characteristic properties, we've successfully solved the macroscopic mystery of the elephant's toothpaste. We know what happened, and we know what substance was produced. But honestly, this leaves us with an even bigger, much more fascinating question to tackle next. Even though we've made this huge amount of progress by reasoning about property changes, we still don't know the hidden mechanisms at play. How exactly are new substances produced at the invisible, microscopic particle level? What in the world is happening between those particles of matter to suddenly create something entirely new? I want you to really think about that, and we'll explore that hidden microscopic world together next time.